So, to start with, I would like to introduce myself a little bit and do a housekeeping statement. So, my name is Mingchao Yu. You can just call me Fisher. I did my PhD in network coding and information theory from Australian National University. So, anyone here from the South Hemisphere? No? Okay, then I'm unique. Yeah, and then last year I joined University of Southern California and did works on distributed computing with Professor Salman Eversmere. And recently I joined Dolby Laboratories because Dolby acquired a startup company I worked with, and as the inventor of all the patents, I am part of the deal. So the PolyShard work I present today has nothing to do with Dolby at all. It is my work did with my colleagues in USC, Dr. Sunze Lee and Professor Salman Eversmere, and collaborators from University of Washington, Professor Sriram Kannan and Professor Pramod Viswanas from UIUC. Okay, so all of us has an information theory background. So when we did our literature review on blockchain and try to understand its scalability, we found that sharding is a very promising and interesting solution with certain trade-offs. Then our information theory minds shout out that, wait a minute, these trade-offs can be solved using information theory. Then here it comes, PolyShard, which is the very first sharding proposal that tries to scale blockchain from the information theoretical perspective. Cool. So the outline of my... Really? They will go backwards. Let me try it.
It did work with this?
Yeah, it did work. But never mind, I can use my keyboard.
Yeah?
Yeah, that's fine.
Okay.
Time's clicking. Okay, so the outline of my talk today. So first I will show you the storage and verification model we are considering and define the performance matrices we are interested in. Little spoiler, we consider security, storage, and transaction throughput. And then I will discuss the scalability of two existing blockchain solutions. And then I will introduce PolyShard step by step, and then summarize my talk. And after that, I will spend 1 minute to talk a little bit about our team and our other works. Okay? So, first, excuse me.
Would you like?
Yeah, will be great. Thank you. Hope they will not confuse things. Yeah, it works perfectly.
It even has a laser. Try not to.
Point to myself. Okay, never mind. So, what we consider is a verification function that involves a ledger and a transaction block and a verification function. So what each node does is it has a ledger, and when transaction comes in, it runs a verification function and make decision, so whether this block is valid or not. Okay? And then the performance matrices we consider, there are three. The first is storage efficiency. We measure how much data or how large is the ledger stored in each node. Because we want it to be larger, the better, so we take its inverse. So it's 1 over the storage size per node. The second metric is throughput, which is the number of transactions we can verify per epoch. The third measure is security, which is the number of malicious nodes this system can tolerate. And here, we will consider quickly adaptive adversaries, which means the adversaries can quickly figure out which node belongs to which shard and do some dedicated attack. Cool. Now, we look at the performance of the black screen. Okay, so first, the classic blockchain system, without any sharding, we call it a full replication system because, say we have 30 nodes, then every node will store the whole ledger, and that when the transaction is received, every node will do the verification, then there are some consensus going on afterwards. For this system, its performance is as follows. Its storage efficiency is 1, because every node stores the same thing, so it's O1, it's a constant. Throughput is 1 block per epoch, which is also constant. But its security is that it can tolerate at least half of the nodes to be malicious. So its security is in the order of n. To be precise, it is n over 2. That means for the classic blockchain system, if you increase the number of nodes, its storage will not reduce, its storage cost won't reduce, its throughput won't increase. It's only that its security will increase. And actually, in real-world system, if you increase the number of nodes, actually the throughput might even reduce. Then here comes sharding. So given, say, we have 30 nodes, and we would like to have 3 shards, say the Netherlands shard, the German shard, the Belgian shard. Then what we do is for the 30 nodes, we assign 10 nodes each for each shard. And then so when transactions of each shard come in, or the 10 nodes of the corresponding shard will take care of the verification. For such a system, so we assume there are q nodes per shard, and the number of shards is k equal to n over q. In here, so q is equal to 10, we have k equal to 3 shards with a total of 30 nodes. For such a system, what is its performance? Yeah, cool. So its storage efficiency is 1 over k ledger per node because we partition the whole ledger into k pieces. So each node only stores 1 over k fraction of the ledger. So the storage efficiency is in the order of n. It increases linearly with n. The throughput is k blocks per epoch because we have k blocks coming in for the k shards. The problem is its security. Because each shard is only handled by 10 nodes, then if I corrupt 5 nodes of this shard under a quickly adaptive adversary model, then this shard will be compromised, which will ruin the whole system. So the security of this system is only O1. It doesn't scale up when we increase the number of nodes in this system. Okay? So in summary, we have a dilemma here. If we use full replication, then we have the highest level of security, but our throughput and storage do not scale. But if we use sharding, then our storage and throughput will scale, but we sacrifice the security. So there is a tension between our security, storage, and our throughput. So in order to solve this tension, we will introduce PolyShard step by step. So our first step is to look at the storage side of the whole system. There actually exists a very handy rapprochement between the storage and the security, which is as follows. So let's consider a system consists of 6 nodes. If we use the full replication system, then every single node store the whole copy of the ledger. It has the highest level of security, but the storage efficiency is poor. Okay? Then if we use sharding, then what we do, suppose we have two shards. Then we partition our ledger into two pieces, say subledger A and subledger B, and we use 3 nodes to store subledger A and use 3 nodes to store subledger B. This one has a better storage efficiency than the full replication. But its security is a bit concerned, because if I attack 2 nodes that stores the ledger B, then there's no way we can make consensus of what's the value of B. Interesting enough, for such a system, there is a very handy solution to achieve storage efficiency and security simultaneously. So if you are familiar with coded distributed computing or anything like Reed-Solomon code, you should already know the solution, which is as follows. So we treat subledger A and subledger B just as 2 giant vectors under some certain field, certain finite field. And in each node, what we store is a linear combination of A and B. So the size of A plus B is equal to A and also equal to B. So it's just a linear combination. So in node A, we can store A plus B. In node 2, we store A plus 2B. In node 3, we store A plus 4B, so on and so forth. So this is actually a Reed-Solomon encoding of the different portions of the whole file. Okay? So under this system, no matter which 2 nodes you compromise, there are still 4 other good nodes that store the true value of linear combination of A and B. So as long as any 2 of them survive, you can recover both A and B. And if more nodes survive, then you can detect the compromised nodes or even correct them. So by using, this is something called redundancy coding in information theory. So by applying redundancy coding on the storage, we can enjoy both storage efficiency and the security. So storage and security can get along with each other through redundancy coding. What about throughput? Do you think throughput can also be scaled using redundancy coding? So what's wrong with throughput? You might think, okay, this thing doesn't work for throughput because once you mix or create linear combinations of the different shards, then the coded subledgers cannot be used to verify transactions, right? Because when you have subledger A, you have the balance of each user, which is understandable. But if you combine the balance of people from shard A and shard B, what's the value stored in that vector? It's not comprehensible, right? So you might think throughput or the verification cannot be done after we encode the subledgers together. But the reality is, no, that's not true. It is still possible to do verification even if we encode the shards. So the key to realize this is something called coded verification or coded computing. So I will introduce coded verification using a very simple toy example here. We consider a very, very simple verification function where R is equal to B minus K, B minus X, where Bx is the current balance of all the users in shard K. And Xk is the fund that all the users in shard K will send out in this epoch. And Rk is the remaining balance of each user after all the transactions get approved. So this block will only be valid if the remaining balance of every single user is greater or equal to 0 after this xk get approved. So our verification function is current balance minus the money to be sent, and we check whether the resulted balance, remaining balance is greater or equal to 0 or not. Okay, so this is our verification function. Now we consider a system that has 6 nodes and 2 sharding. That means we will have shard 1 and shard 2. So say we use node 1 to 3 for shard 1, then all these 3 nodes will do the same thing, which is the current balance B1 of all the users in shard 1 minus x1, which is the submitted block for shard 1, and calculate R1. And then they make consensus to see whether this block should be approved or not. And then for similarly, node 4, 5, and 6 will all work on the second shard to calculate R2 equal to B2 minus X2 and make consensus to decide whether we should accept X2 or not. Then the problem is obvious. If I compromise 2 nodes in shard 1, then shard 1 is compromised. Okay? Now, we have a new idea. So what we do is every node has a linear combination of both the ledger B1 and for shard from shard 1 and B2 for shard 2. So see, the balance here is B1 plus B2, B1 plus 2B2, B1 plus 4B2, just as what we just showed for the storage. And also, for the incoming transaction blocks x1 and x2, we apply the same coding. So node 1 has x1 plus x2, node 2 has x1 plus 2x2, node 3 has x1 plus 4x2, so on and so forth. So each node has a linear combination of the balance of all the shards, and it also compute a coded block, which is a linear combination of all the blocks from each shard. And the result, the remaining coded balance is, as you can see, node 1, its computation result is R1 plus R2. Node 2's result is R1 plus 2R2. Node 3, the result is R1 plus 4R2, so on and so forth. As long as any two of them survives, we can recover both R1 and R2. So to achieve this, the nodes, once they finish their own computation, you just share with each other their coded results, and then they apply decoding, which is basically solving linear equations, to find out both R1 and R2. And this system is robust as long as any no more than 2 nodes get compromised. So this is a toy example of coded transaction verification. At a high level, what we do with coded computing is as follows. So we have a function f, which takes a vector x as input and an output vector y. We would like to evaluate this function for k times. So y1 equals to fx1, y2 equals to fx2, and up to yk equal to fxk. So in a traditional way, what we will do is we will find k nodes and assign each x to each node and ask them to compute the corresponding y1 up to yk. In sharding, what we do is we assign multiple nodes for each computation task. But in coded computing, what we do is as follows. So given all the k inputs, x1 up to xk, we create uncoded inputs and assign these uncoded inputs, which is w1 up to wn, to n different nodes. And these n nodes will compute n results. It turns out that the uncoded results here are actually linear combinations of our desired y1 up to yk. So the core of coded computing is to inject redundancy to the input so that the output at all the nodes, they are linear combinations of our desired outputs so that we can decode our desired output through linear decoding. Okay? So in order to achieve this, my colleagues Yu Chen invent a coding technique called Lagrange coded computing, which is the algorithm that achieves such coded input leads to coded output property. And this algorithm works for any function that is a multivariate polynomial function. So what we do is as follows. Given the k inputs, we create a polynomial that pass all these k nodes. And then the coded inputs are some randomly picked values from this polynomial. So if I use animation, so we have the k inputs, we find out a polynomial that pass all these nodes, and then to create the coded inputs, we just pick some random points in this polynomial. And because both x and w are belong to the same polynomial, if we drop them into a polynomial verification function, the output, coded output z and our desired output y, they actually also belong to the same polynomial. So in terms of decoding, what we do is as follows. So each node will do its computation, and we gather its output, which are some points in this chart, z1, z2, z3, up to zn. Some of them might be missing, and some of them might be wrong. So based on these points, we find out the polynomial. See? So some of the values are correct, some of the values are wrong, and maybe some of the values are missing. But as long as there are enough correct outputs from the nodes, we can recover the polynomial. And our desired y1 up to yk are actually the evaluation of this polynomial at its first k inputs. So this is Lagrange coded computing that allow us to create a redundancy for the input and obtain a redundancy at the output, which allow us then to decode stuff. So how will coded sharding looks like if we apply such redundancy? Now, imagine we still have 30 nodes and 3 shards. Now, each node here will store a coded copy of all the 3 subledgers. And when the 3 transaction blocks are received for all the 3 shards, each node will compute a linear combination of all the 3 blocks and then apply the verification function. Once they finish the computation, they will share with each other their results so that each node can apply polynomial decoding to recover all the function results, which is the output of the verification function. Then you can decide whether each block is valid or not and to include them. So in more mathematically, what happens is as follows. So whenever, in each epoch, we receive k blocks from the k shards, then each node creates a linear combination of all the k blocks and create a coded input to the verification function. Then you pass the verification function, the input to the verification function, and then it will share with each other the verification result. And then once each node receives all the output of all the nodes, it will decode the decision of each shard and then create a linear combination of all the valid blocks and include it in its own chain. So the chain stored in each node is also coded. So it's the coded version of a ledger. Okay. So main theory is the performance of PolyShard. So given a blockchain system with n nodes, and μ% of them are malicious, and the verification function has a degree of d, then our PolyShard can support k equal to this many shards, which is linearly to the number of nodes n. And its storage efficiency, it's also a function of the number of nodes, the degree of the verification function, and the malicious percentage. And it is also linearly to the number of nodes n. Also, its security is similarly a function. It's linearly to n. So in summary, full replication achieves a linear scale of security, but not storage and throughput. Our uncoded simple sharding achieves storage efficiency and throughput scaling, but not the security scaling. But PolyShard can achieve linear scaling of both storage, throughput, and security. And it turns out that from information theoretical point of view, this is the best you can do when your number of nodes increase in a system. So PolyShard allows all the three performance matrices we consider to scale linearly. And we also did some simple simulation to test the performance of PolyShard. So the verification function we use is what we just mentioned in the toy example, where we look at the current balance of each shard and subtract the money to be sent and look at the remaining balance of each sender to see whether the block is valid or not, based on whether all the sender will have a remaining balance of greater or equal to 0 after the transaction. Okay? And we plot the throughput of PolyShard, the full replication, and sharding against time and against the number of nodes in the system. So as we can see, when time goes, our epoch increases, our train length increases. So the time it takes to calculate the current balance will increase, and that's why the throughput of all the schemes will reduce over time. But we always achieve a gain of 50x, which is the same as simple sharding, because we have 50 shards. And when the number of nodes increase linearly, we can see the throughput of both PolyShard and uncoded simple sharding increase linearly with the number of nodes, while the full replication, the classic system, its throughput is a constant. Okay? So summary and future extensions. So from information theory perspective, replication is an inefficient way of doing redundancy coding. So full replication sacrifices the storage and throughput scalability, and the replication within each shard will increase the storage and throughput scalability at the cost of security. But in PolyShard, we will use polynomial redundancy coding for coded storage and coded computing, so that it will achieve the optimal scaling of both throughput, storage, and security. And so far, our polynomial PolyShard supports any verification function that is a polynomial. So our development is still in early stage, so there are tons of future works we plan to do. For example, we will try to support the cross-shard transactions, to support non-polynomial verification functions, and to improve our polynomial encoding and decoding efficiency, and to improve our efficiency under network dynamics in synchronized and asynchronized settings. Okay, so that's all for PolyShard. So before we go for lunch, please excuse me for 1 minute for me to describe our team and some other works. So this work is done under a startup company called Applied Protocol Research, which is staffed with renowned academics from different universities with various backgrounds, including Andrew Miller and David Shea, which is kind of the father of information theory. And also my supervisor, Professor Salman Avasmia. So PolyShard is one of our attempts to scale the blockchain. So the other project we are currently working on is called Prism. So at high level, the Prism protocol, it is a DAG-based protocol system, and it deconstruct the blockchain by separate the different functionalities of the blockchain, like verification, transaction proof, block approve, leader selection, and voting into different parallel functionalities so that all of them can run in parallel. The result is remarkable. So when the adversary power increases, its throughput actually decreases linearly with the capacity of the channel. So when there is no adversaries, the Prism system can process transaction, which is equal to the bandwidth that the number of transactions the network can allow to be delivered. So its throughput decreases linearly with the adversary power, which is optimal. For latency, it's when the security parameter increases, its latency is constant up to a point, and its latency increases slightly after a certain point. But on the other hand, the current Bitcoin system, its latency will increase very quickly at a very much earlier stage. So this is the other work we are currently working on. So that's all from my talk. So if you have any question related to PolyShard, you can contact me. For the team, you can contact Professor Pramod Visvanas. Okay, thank you very much.
Excellent.
Yeah,
thank you, Fisher. That was really interesting. We have time for a few short questions. Mustafa?
Could you clarify, so are you applying the sharding per block, or are you sharding the entire state of the blockchain in like one big coding?
Yes, so we shard the whole blockchain and apply coding. Each node will not only take care of its own shard, it will take care of all the shards through coding.
Right, so you have like one big code and you update that code every single update,
What do you mean by update?
every time the state of the ledger changes, you update that code.
What do you mean by herd? The herd is all the nodes?
No, by the state of the shard.
Yep.
So you have a big code per shard, and do you update that code every time a new transaction comes through?
Yes.
Okay. So with recent sharding proposals, the consensus nodes in the shards, they're not responsible for storing any of the state in the shard, because they effectively run stateless clients. And so the job of actually storing the state and the storage is basically anyone who wants to run a full node, anyone that wants to validate the blockchain, but they don't have to be part of the consensus. And that's necessary because if you keep reassigning nodes to shards, then you can't have nodes download the entire state because it's not really sharded anymore. So my question is, do you think that this could potentially be applied, this sharding scheme and verification scheme could be applied to clients or full nodes that are running independently and verifying the blockchain, as opposed to the consensus nodes in the shard themselves?
Yes, so currently we only consider the full nodes, which can get access to all the shards and all the blocks. We currently do not consider the clients.
No, I mean, by full nodes, I mean clients. So, to clarify, I mean, you're sharding among the consensus participants in the shard, right? But in recent sharding proposals, the nodes in the shards that are participating in the consensus, they don't store any state. They basically run stateless clients. So there's no need to apply sharding for there's no need to shard the storage for the consensus nodes. Instead, it's simply the clients, the end clients that store the state. So my question is, could you adapt this system in the future to apply the polynomial encoding, I mean the erasure coding, to the clients, so that clients only have to store part of data to be able to verify transactions?
Yes, I think so. I don't see any problem there. Yeah.
Cool.
Thank you. I have another question. Could you pass through this mic, please? Thank you.
Hi, Philip.
Hi, thanks for the presentation.
Yeah.
I was wondering which kind of verifications I can perform, like for example, to add to your toy example, you check that the balances match up, but could I also check that the signature, for example, is correct or something like that?
Yes, good question. So currently we only support verification functions that are polynomial. The classic signature verification functions such as the elliptic curve ones, they are not polynomial. So there's no native support to them currently. But the good news is there's something we can do is come on. Okay, anyway, so there's a recent paper showing us that any function that works on the binary field can be extended to a polynomial over a higher field. So that means if we want, we can convert literally any function into a multivariant polynomial function and then drop our PolyShard on top of it. But that is kind of inefficient because you do field extension, which is very time-consuming and costly. So we try to work out the polynomial sharding that natively support non-polynomial functions, as I mentioned in the future work.
Are there any further burning? Okay, all right, let's do it.
Yeah.
There's a microphone in the back. Thank you.
Yeah, I have a question. So the way where I see the problem in the network, it's not the size of hard drives that's limiting, it's the network throughput. Like we're limiting block size not because our hard drives are full, but because network latency and sort of uncle rate or whatever you want to call it. So my question is, your scheme seems to need every node to get all the blocks from all the shards. So yes, they only store 1/k of the state. So they save on hard drive space, but we're not saving on bandwidth at all. So because every node to calculate its linear combination needs all the blocks from all the shards, isn't that really the limiting factor that we need to minimize rather than the storage requirement?
Yes, so communication cost is something we pay for PolyShard because in order to encode all the shards, then you need to download
all the blocks.
Yes, to initially. But later you don't have to download all the K shards.
No, but on an ongoing basis, you always need all the blocks from all the shards in order to...
Yes, all the blocks, yes.
Yeah.
Yeah, but one way to accommodate this or to alleviate this problem is to do sparse coding. That means you don't encode all the shards, you only encode say 10% of the shards, all the blocks, so which will reduce the bandwidth consumption. So currently we encode all the blocks from all the shards, but there are a sparse coding that we don't need all the blocks. Yeah, but yes, communication cost is something we pay in PolyShard.
Thank you. All right, great.
The more the merrier, please.
Of course.
If a shard gets corrupted, and you have a cross-shard transaction, how would you avoid the breaking safety?
Okay, so far we haven't looked into cross-shard transaction yet. Yeah, so I can't answer the question for now.
There's a quick question, maybe this is obvious, but so you're with your balance checking mechanism, you said that you're basically checking that the transactions. Sorry, I'm not pointing at anything. The transactions in the block are not spending more than the value in the shard. But doesn't that only prevent someone stealing more money than there is in the shard? But it doesn't validate it on a per transaction basis. So couldn't a user still submit a transaction that spends more money than they're allowed to, but not more money than exists in the shard?
I'm not sure whether I get your question correctly. Could you please repeat?
Yeah. Okay. Does your balance checking mechanism prevent users invalid transactions on an individual basis?
No, it will verify them as a block. So if one transaction is invalid, then the whole block will become invalid.
But I thought you said your balance checking mechanism checks if the value of all the transactions in the block is greater than how much value there is in the shard. So
yeah. So every client's remaining balance. Yeah. Not the sum.
Oh, okay.
Yeah,
I see.
So every single user's balance must be positive or non-negative after the transaction, not the sum of them.
Oh, I see. Thanks.
Yeah. Great.
Thank you. So clearly this has sparked a lively discussion, which is great. Fisher will be here also during the lunch break and for the rest of the afternoon. So if you have further questions, please feel free to ask him. We're going to break now for lunch, and we will reconvene at 2:30.
Okay. Thank you.
Thank you.